Exponential functions are a critical way to model things in life like money, populations that grow and decay. We've seen how to take the derivative of these functions to find their rates of change. Let's flip that around and integrate them to find their accumulation. So let's look at how to integrate exponential functions. We'll start off with the kind of parent of the exponential function, which is e to the x. So we know that the derivative of e to the x is e to the x. We've established that before. So we also know that the derivative of any exponential function of a base a, so the derivative of a to the x power, is the natural log of a times a to the x. So since integration is the reverse of differentiation, if we integrate e to the x, we should get the original integrand. So the integral of e to the x dx is, as you expect, e to the x plus c. And we can check that, of course, by taking the derivative. The derivative of e to the x is e to the x. The derivative of c is 0. Let's try and establish what the integral of any function a to the x with a base a is. So since the integral of e to the x dx is e to the x plus c, a logical place to start for the integral of a to the x dx might be a to the x plus c. So let's try it. So if this is truly the integral of a to the x dx, then if we took the derivative of a to the x plus c, we should get a to the x dx. Well, when we take the derivative of a to the x, you'll recall that the derivative of a to the x is the natural log of a times a to the x. So the derivative of a to the x plus c would be the natural log of a times a to the x dx. Not quite what we have in the original integrand, but very close. The only difference, this constant. So the way to get rid of that constant is by dividing it out, because this works except for that natural log of a. So let's divide out by the natural log of a and see if that works. So the integral of a to the x dx equals 1 over the natural log of a times a to the x plus c. So if we took the derivative of this, the natural logs would cancel each other out, and we'd wind up with a to the x, which is our original integrand. So this finding leads to two general rules for integrating any exponential function of any base, including e. The integral of a to the x dx is 1 over the natural log of a times a to the x plus c. The natural log, this is sort of a conversion factor to change it from e to the x to any base. And we can also, just like we have handled other more complex functions, where it's not just a to the x, it's a to some function of x, where u is the function of x, the integral of a to the u du is 1 over the natural log of a times a to the u plus c. We do have to have the du in there for that to work. So those are our general rules for integrating exponential functions of any base. With those rules in mind, let's go ahead and work through some examples. The integral of 2 to the x dx would be 1 over the natural log of 2 times 2 to the x plus c. And we could check that by taking the derivative, because the derivative of 2 to the x is the natural log of 2 times 2 to the x, and the derivative of c is 0. And so the natural log in the numerator and the natural log in the denominator would cancel each other out, and we'd wind up with 2 to the x dx. The integral of 3e to the x dx, using the constant multiple rule, we can move the 3 out front. That's equal to 3 times 1 over the natural log of e times e to the x plus c. Now, if you remember the simpler rule for e to the x, the integral of e to the x, then you don't even need this part. But I'm showing you this to show that this does work for base of e, because, of course, the natural log of e is 1. So this entire fraction cancels out and becomes 1. And in the end, our answer is 3e to the x plus c. And we can very quickly take the derivative of that, because the derivative of 3e to the x is 3e to the x. So the integral of 4x e to the x squared dx, we've got a little bit more complicated situation here. So now we're going to use that rule that the integral of a to the u du is 1 over the natural log of a times a to the u plus c. So for this to work, though, we have to have a function, u as a function of x, and then we have to have that du part in there. So let's look at it. If we let this power here of e be equal to u, so u is equal to x squared, then du is equal to 2x dx. And indeed, we do have something like that here. We have an x to the first power here in front of the e term, so this is going to work. We do need to simplify that a little bit, so to get x dx by itself, we're going to move the 4 out front. So if du is equal to 2x dx, then 1/2 du is equal to x dx once we divide both sides by 2. So we've accounted for e to the u, and then x dx is equal to 1/2 du. And we move the 4 to the outside. So we've got the e to the u term, and we have the du term. And moving the 1/2 to the outside, this becomes 2 times the integral of e to the u du, which is 2e to the u plus c, remembering that the natural log of e is 1. If this were a different base, we'd have to have that 1 over the natural log of the base term in here. But since the base is e, we don't need that. Therefore, the answer, once we resubstitute back in, everywhere we see a u, we put an x squared. The final answer is 2e to the x squared plus c. And to check that by taking the derivative of 2e to the x squared is 2 times e to the x squared times the derivative of x squared, which is 2x. So that becomes 4x e to the x squared. We'll look at additional examples along with some real-world applications of this in class. We've examined how to find the integral of exponential functions of any base, beginning with e to the x, then expanding to a to the x, and even more complex functions where a is raised to a function of x.